So another form of bearing that you're going to need to know about is thrust bearing. Uh, so the other, a typical journal bearing is able to resist force that is acting perpendicular to the axis of rotation. Thrust bearings do the opposite. They are able to resist forces that are acting parallel to the axis of rotation. So typically speaking, we usually have is setups like this where we got these pads here. Those pads can be installed such that they're kind of at a fixed angle, or they can be installed so that they have the capacity to tilt as they to tilt, so that they kind of adjust the angle to match basically kind of what is needed to resist the thrust that's being generated for the speeds we're talking about. So as you do that, obviously you're gonna set up, you're gonna have a certain velocity profile in going on between the two surfaces that are moving relative to one another. So then basically as the fluid kind of moves in here, it gets squeezed in, and we're setting up a pressure distribution. Now, of course, that pressure distribution isn't going to be constant kind of across the entire cross section here, because the velocities aren't going to be constant. So like the velocity profile in increase the kind of the magnitude of the velocity profile also increases with the radius, because obviously the outer surface of the of the disk that's moving is going to be moving faster than the inner surface here. But yeah, so anyhow, this pressure distribution that gets set up is going to be pressing to separate the thrust bearing pads and the disc that it's pressing against. So oftentimes these will be necessary if you're going to be, especially if you're going to be using okay, if you have a propeller or something like that, then obviously you're going to need to have some sort of capacity in order to transfer that thrust from the propeller to the rest of the ship or the aircraft, or whatever it is that you got the propeller mounted to. If you are using helical gears, then those generate a certain amount of axial thrust, and you need to be able to resist that thrust in order to, ensure that the shaft with your axial gear on it doesn't shoot out of your engine. So those can also be used set up like this, where we have kind of a solid um, bearing can be used as well. So those types of bushings, so there's certain types where we can use what we call boundary lubricated bushings. So those are relatively common. So basically, what happens here is you have some sort of porous metal, often created by sintering the material, create the bearing by sintering the bushing, and then there's going to be little gaps inside, and then basically you immerse the bushing in oil of some sort, and that creates that basically impermeates the gaps in the metal, and ensures that there's always going to be some lubrication available. And you're using materials that have relatively low coefficients of friction generally. Typically speaking, we're usually talking first. We're usually talking for relatively low loads. or situations where the friction isn't quite as critical, but there are essentially operating limits that can work with. So operating limits for static loads, operating limits for dynamic loads, and then the velocity comes into play there too. Uh, so the velocity will be the relative velocity between the bushing and uh, the journal is, I guess, the shaft itself, where they're in contact. So you're going to have limits on what you can expect to see uh, capacity for that, based upon the pressure and based upon the velocity, and also based upon multiplying those two things together. We've also got non-metallic bearings, so phenolics, nylon, uh, polycarbonate, rubber, wood. So, obviously some of them are going to be better than others, uh, but you can have different pressure ranges available. Some of these are less applicable for higher temperatures, so we don't want to be using uh, boundary lubricated wood if it's going to be burning. And then, of course, again, the velocity and the pressure times the velocity comes into play there as well. And finally, we've also got ball bearings, roller bearings. So these are good because they're relatively low friction, um, especially when we're talking compared to your journal bearings. When you're talking an S value that's low, we tend to see. Actually, well, sorry, that wasn't the S value. That was the viscosity times the rotational speed divided by P. We tend to see the friction kind of starting off high, dropping off, and then increasing. So if we're operating in this region a lot, if we're operating in low speeds, uh, low speeds or very high pressure, then we may end up being in situations where you're not able to develop that full hydrodynamic wedge that you rely upon in order to reduce friction and especially to reduce wear. So when you're in this region here, the wear is, well, here. Okay. When you're in this region here, the friction is being caused by metal on metal contact, and that's causing a lot of wear. So using a roller type bearing can, a ball bearing or a roller bearing can help you a lot. They are, unlike journal bearings, we are talking lifespan limited by fatigue. So again, the balls or the rollers are going to be seeing alternating and alternating stresses as they roll around. So that's eventually going to lead to fatigue failure of your bearing. So typical way that works is that the load times some sort of the load times the lifespan to the power of 1 over alpha, where alpha is going to be typically 3 for ball bearings or 10 over 3 for roller bearings, is equal to some sort of constant. So that bearing life is basically the number of rotations, and they're typically measuring that kind of how many rotations will 90% of the bearings at that load have failed. So generally speaking, when you're working with your manufacturers, they're going to give specs in terms of what we call a catalog rating load. And that'll be basically the load at which they measured the performance of this bearing, and they will tell you how long that bearing is rated to last at that load. So, and then basically you just kind of plug it into this equation here, where you need to take into account the catalog rating versus for the load versus what desired load it is that you want. And then they're going to tell you like the rating life in hours, and that will have been done at a particular rating speed. And then obviously you need to take into account the differences between that if you want to be operating at a different speed as well. And then basically from there you can solve for how long you should be able to expect in hours your that component to last based upon your operating conditions compared to the catalog rating. And yeah, so those yeah, those can be quite useful too. Yeah, and that's it for now.